And the main topic today is going to be system calls. Okay. So last time, we showed this picture of an operating system, how the operating system stands between the hardware and user programs, and the operating system implements multiple services, and user programs have access to these services through system calls. So the application program would issue a system call in order to access system services. These services, some of the services are services that the user can interact. The user interacts with, like user interface, program execution, I/O operations, file system manipulation, communications, like message passing and shared memory. And in this course, shared memory is something that we will be covering in assignment number 1. Assignment number 1, we will be using shared memory. Also, error detection. Obviously, the system has to be aware of all the errors that will occur in the system, whether they are user errors or device errors, and do the right action, handle that error properly. Another set of services, operating system services, are not visible to the user, and they have to do with the system itself, like resource allocation and resource management, managing hardware resources, accounting information, protection and security, like memory protection. We talked about memory protection in previous lectures. If a process tries to execute an out-of-bound memory access, this will generate an exception, and the hardware will give control to the operating system by invoking the corresponding interrupt service routine, ISR, and that will give control to the kernel, and in this case the kernel will protect the system by terminating the offending process. User interfaces. So in terms of user interface, there is a command line interface and there is a graphical user interface. So in the earlier days, there were only command line interfaces. When I started using computers, we only had command line interfaces. Then some systems started to offer a graphical user interface, which is what you guys are familiar with, the graphical user interface with all the features like windows and menus and mouse clicks and even touch screens. So that's graphical user interface. In terms of command line interface, in this course you'll have to do some command line interaction with the system, and we assume that you are familiar with this because CSC 60 is a prerequisite for this course, and in CSC 60 you should have done some command line interaction and some script programming, some scripting languages and make files and things like that. So you'll have to do some of this in the programming assignment. You'll need this. Okay, so graphical user interface, there isn't much that I can say. It's everyone is familiar with this graphical user interfaces. Now system calls. So a system call is just a function call. So a system call is a function call, but it's a special kind of function call. what makes it different from other function calls? It's not just what happens, when you make a system call that doesn't happen when you make a regular function call. What are the things that happen when you make a system call and do not happen when you make a regular function call?
Interruption.
What kind of interruption?
Interruption, like it will stop the process and hand over the CPU to run.
Yeah, exactly. Yeah. So system calls, as we said, are implemented as interrupts. And when an application program makes a system call, the control of the CPU will get transferred to the kernel. So this is an application program. P makes a system call. Now the kernel is running on the CPU. So it's a system call is a special kind of function call that causes this change in possession of the CPU. Now the kernel is in possession of the CPU as opposed to the process. And now we are in kernel mode. Remember the mode? When we talked about the mode bit, the hardware mode bit, the mode is going to change from user mode to kernel mode. This is kernel mode, this is user mode. Yeah. So it making a system call will result in this change, which means now the kernel is in charge and the kernel is going to execute that function, the implementation of that function. So it will perform that service and then it will return the results to the application program. Now, usually we do not use system calls directly. Usually system calls are wrapped by application program interfaces, APIs. API stands for application program interface. And usually system calls are wrapped with these APIs for two different reasons. There are two reasons for doing this wrapping. The first is convenience, and the second is portability. So two different concepts, convenience and portability. Now, convenience, it's more convenient to use APIs because APIs are usually more user-friendly and easier to use. And in many cases, they have fewer parameters that you have to pass to them. So, but an API is implemented, is actually implemented by making a system call. So it's just a wrapper. You can think of an API as a wrapper of one or more system calls. So an API may be implemented using multiple system calls. So you may package multiple system calls with one API that does multiple, that requests multiple services and that performs multiple tasks. So APIs are usually more user-friendly. They are easier to use because a system call may have many parameters, like a system call may have 10 parameters. And some of these parameters may not be interesting for the user because usually all users are going to set these parameters to the default values. So there are certain default values that 99% of the time are the settings that you want. So an API will just set these parameter values to those commonly used defaults that are used 99% of the time. And then the API will only require from the user specifying 3 or 4 parameters. So it's just a wrapper that will make the system call easier to use. So that's one thing. The other thing is portability. We have some standard APIs like POSIX, which we will be using in this course, in the assignments. In the assignments, we will be using the standard POSIX API, and POSIX stands for, what does POSIX stand for, given what I have just said? So what should the Letter P stand for portability. Yeah. So it's a portable operating system interface, which means that it's a standard interface that can be implemented on multiple systems, and indeed POSIX is implemented on multiple systems. So POSIX is implemented on multiple Unix systems, Unix and Linux systems, different kinds of Unix systems, and it's also implemented on Mac, on the Mac systems, and and I think it's also implemented on Windows. I have never used it on Windows, but I think there are recent implementations on Windows for the POSIX API. Okay, so this is a standardization, right? So it's one common API that is implemented on multiple systems. So we will use it in our programming assignments. So we will use the POSIX API. In theory, if you write a program using POSIX on Mac and you run it on a Unix system, it should run. But we don't live in a perfect world. So sometimes this doesn't work. There are some compatibility issues. So sometimes there are some differences that will cause your program to that uses the POSIX APIs to function correctly on one platform, but to have a problem on another platform. So that's why for the programming assignments we ask you to make sure that your program functions correctly in our standard ECS computing environment. To make sure that we standardize things. But in theory, with the POSIX API, if you use the POSIX APIs, it should work on any system that implements POSIX. So this is true 99% of the time, maybe. But because the implementations are not perfect, or because there are some subtle differences between the different implementations, maybe 1% or 0.1% of the time, there will be a problem. Okay. So in addition to POSIX, the POSIX API, there is the Java API. So Java is a language that is implemented on many different platforms. And when you use the Java API, in Java there are lots of functions that you call and that use the system that are implemented using system calls. Anything that is that involves an I/O, or a file access, that's implemented using system calls. Anything that we know that cannot be done without OS interaction, OS intervention, we know that it must be implemented using a system call. Okay. And there is also the Windows API as well. Now here's an example that shows us how an application, a typical application, will make many system calls, will require many system calls, regardless of how these system calls are called. So they are not necessarily called directly. You are not calling the system call, the actual system call directly, but you may be using the APIs that the APIs of the programming language that you are programming in, or the library that you are using. So if you are using Java, then you are using the Java system, the Java APIs. If you are using the POSIX library, then you are, or a library that implements POSIX, then that's your API. So this is an example of a program that copies from one file to another. So this program will first prompt the user to enter the name of the input file. So prompting the user means printing to the screen. Printing to the screen cannot be done without operating system intervention, which means that no matter which APIs you are using, this will be implemented as a system call. You have to go through the system because access to I/O devices is restricted to the system. Then you will need to read the name of the input file from the user. And reading that from the user from the keyboard, again, you must go through the operating system. So this is implemented as a system call. Then same thing applies to the output file. You prompt the user to enter the name, then you read the actual file name. Then you open the input file. Opening a file is a system call. If it doesn't exist, you will print an error message, and printing that error message is a system call. Aborting, exiting is a system call, or is implemented as a system call. Same applies to the output file, creating an output file. Then the main body of this program is a loop that reads from an input file, whether it's character by character or string by string or whatever, reads from the input file and writes to the output file, and all of these are system calls. Okay? So this is just an example to show you how an application may be making many, many system calls. And think of all of these changes on the CPU. So whenever the system is requesting these, it's requesting a service from the operating system, and the operating system is running on the CPU, and we are switching mode, and all of this is happening behind the scenes. So, when part of this, one of the objectives of this course is to be aware of the operating system and what the operating system does, and to be aware of operating system intervention, even though it may not be obvious to the application programmer, or it may not be visible to the application programmer. So we should be aware of operating system intervention. This is an example of a standard API. This is just an example. And this example is the read function call that is supported on Unix systems. If you are programming in C under Unix, you will use this read. Well, it's one of the options that are available to you to read from a file. It's not the only option. So there is read and there is formatted read. So there are multiple functions that are available for you, but they're all implemented as system calls because you cannot read from a file without going through the operating system. So this read, it takes 3 parameters: the file descriptor, a pointer to a buffer that you, as an application programmer, is responsible for allocating. And by the way, when you allocate it, you are making a system call. When you dynamically allocate a buffer, you're making a system call. And then you pass the size of that buffer, right? So that the system, so if you allocate a buffer that of size 1K, you want to pass this size to the system so that the system only writes to 1K, knows that it can write, there's only 1K allocated, and it doesn't go beyond what has been allocated. In C, it's the programmer has a lot of responsibility. So it's, you are responsible for allocating the right size, and everything is explicit, and there is less automation in C. And then it returns this function call. This API returns the size of the data that has been read or that has been written to the buffer. So question, you pass a file descriptor. Where will this file descriptor come from?
User.
So you just give it a number. How will it know to open the file that you want to read from? How will it know to read from the file that you want to read from? So this file descriptor is specifying the file, right? So when you read from a specific file. How will it know? How will the system know that which file you want to read from And you are only passing a file descriptor. You are not passing a file name. So, has anyone used read? Okay, so logically, where should that file descriptor come from? The file descriptor is just a number, an integer, for that file. So, but where will that come from? Yeah.
Isn't it from open?
Yeah, exactly. So before you do read, you have to open the file. So you do open, and with open, you pass, among other things, the file name. You pass the name of the file, and then open returns the file descriptor. So you tell it, I want to open this file, then it returns to you an integer, a number, an ID for that file, so that you can use in subsequent references to the same file, and subsequent references are the reads and the writes. Then you close it. Then when you are done with it, you close it. Okay? So it's this is just an example. Now, when in implementing system calls, the system will have has a system call interface. So the system call interface is the interface between the application programs and the actual system calls. The system call interface will have just a table, because each system call has a number. So usually the implementation is a table indexed by the system call number. And for each system call number, there is an entry with the address of the corresponding function within the system that implements that. So all of these are in kernel mode. So system calls are implemented in kernel mode, but the call, which is the system call or the API, is issued in user mode. Parameter passing. How do we pass parameters to system calls? There are at least three different methods. One method is passing the parameters in registers. And what's the problem with this? Passing parameters in registers.
The number of registers.
Yeah, the number of registers is limited, so this will limit the number of parameters. And usually not all registers are available for parameter passing. Only a subset of the registers are available for parameter passing, and that's very limited. So in order to solve this problem, people came up with other solutions. One solution is putting all the parameters in a memory block. You put all the parameters, parameter 1, parameter 2, parameter n, as many parameters as you want in a block, and then you pass the address of this. You pass the address of the block in a register, in one register. Another method, an alternative method, is pushing parameters on the stack and having the system pop them. So it's one standard method for passing parameters is the caller pushes, the caller does a push, and the callee does a pop. And in this context, the callee is the operating system. Types of system calls. Of course, we'll not have to. We'll go through these examples of system calls, and we will just point out that some of these will be used in our assignments. Well, for example, file management, opening files, reading, writing. We will be using file management in the assignments. Device management, reading and writing. So these are among system calls, because what we will be using, we'll be writing to the screen and reading from the keyboard. So we will be accessing I/O devices. information maintenance, like getting the time and the date. And in some assignments, we will be doing timing. Timing of different methods for doing the same thing, using different methods, and measuring the time for each method and comparing them to see which method is faster. So in order to do the timing, we will need to get the system time. So this will involve system calls. Communications, as I said previously, we will be doing, we'll be using shared memory in assignment number 1, and that's a communication method that we will be using. And message passing is something that we will not be doing we will not be using in the assignments, but we will be studying the concept. Operating system services or system calls for protection, control access, setting permissions, like setting permissions to files. So these are examples of system calls. And here are some examples of actual system calls. So actual system calls on Windows and Unix. For example, on Windows, there is a system call for creating a process. It's called create process. On Unix, there is fork. In our assignments, we will be using Unix. So we will be using the fork system call. Okay. In a later lecture, when we get to processes, we will look into the difference between fork and create process. We'll have some examples. We will look into some examples on how a process is created using create process and using fork. So there are some differences. We will look at those. But in the assignments, we will use fork. Waiting, so we will be using waiting. Wait for single object and wait on Unix. We will be using wait in the assignments. Create file, the corresponding system call on Unix is open. As you can see, the system call names on Windows are longer and more descriptive than the system call names on Unix. Okay, so we will be using some of them, not all of them in the assignments. And this is an example that shows you or reminds you of the fact that even if you use standard library functions that access input-output devices, like the printf library function in C, that printf library function, because it accesses an output device, it must go through the operating system. So it is implemented as a system call because it's the standard C library will translate this into the right system call that writes to the screen. So just the idea here is that some of the standard library functions that you use in the language that you are programming in, whether it's C or C++ or Java or Python or whatever, they are implemented as system calls. Okay, so now let's learn about system programs. What are system programs? Well, system programs are programs that belong to the operating system but are not part of the kernel. So they are like extensions of the operating system, and they may run in user mode, not in kernel mode. But system programs may involve many system calls. So in a system program may be issuing many system calls, and whenever it makes a system call, it's switching to the operating system, and the operating system is running in system mode. But system programs are typically run in user mode. So examples of system programs. System programs for file management, like text editors. A text editor is a system program with every operating system. There is at least one text editor, and many operating systems have multiple text editors. Like Notepad on Windows and VI, or Pico and Emacs on Unix. So these text editors, these are not part of the kernel, but they are system programs. And usually they make lots of system calls. So it's part of the system, but it's not part of the kernel, but it makes lots of system calls. File management, status information, programs that give you information about the status of the system. File modification. So I mentioned text editors in the previous slide. Well, file manipulation means creation and copying of files. So file management is creating a file and deleting and renaming, and the file manager basically is what we mean by file management. While file modification, an example of a system program that does file modification is a text editor. That's a system program. Programming language support, like compilers, assemblers, debuggers, interpreters, linkers. So these are system programs, but these are not part of the kernel. And usually there is a compiler that comes with an operating system, like Unix systems are distributed with the GCC compiler. Okay. But that compiler is not part of the kernel. Loaders, communication programs, etc. So these are examples of system programs that the user interacts directly with, and in fact the user loads. So when you use a text editor, you actually load it. You actually click on that text editor if you are using a GUI, or you invoke it at the command line as a user. But there are system programs that you as a user the user does not launch. They are launched by the system itself. They may be launched at boot time, so there are system programs that are launched at boot time, and then when they complete their tasks, they terminate. And there are some system programs, some background system programs that the system creates, and they stay all the time. As long as the system is active, these programs are running in the background. Examples are programs that keep checking on the disk or checking on memory. So these are running in the background, and they are performing system services. So the user did not create them. They got created by the system, but they are not part of the kernel. So when you look at your task manager in Windows, you will see a bunch of processes, a bunch of programs that you did not create as a user. So these got created by the system. Background services are sometimes called daemons. Okay, so now that ends our discussion of system calls.